All right, so as you saw that entropy measures disorder in the system. And what we learned from the second law of thermodynamics was all the processes that occur in nature occur in a direction, occur because in those processes entropy either stays the same or increases. In all natural processes, entropy increases. Okay, so if in a process entropy would decrease, nature doesn't allow that process. You don't see that in nature, occurring in nature. Okay. And what we are going to see here in the next few slides is, even though that those processes are possible where entropy would decrease, the probability of them happening is almost negligible, negligibly zero. And so this is a probabilistic view of that statement. Okay, so what we are working towards is the following. So here's the expression that Boltzmann derived for entropy. Now this is a very hard calculation. What this expression says is the entropy of a system is equal to a constant. We name this constant after Mr. Boltzmann. Okay, so it's a Boltzmann's constant times natural log of the number of microstates compatible with a given macrostate. Okay, so what this means is, so if there's a gas, let's say the atmosphere in the lecture hall, which is at 20 degrees Celsius, okay, and 1 atmosphere pressure. So that's the macrostate, and the 20 degrees temperature and pressure are uniform throughout the room. For that macrostate, how many different ways can you arrange all the molecules in the room? That's the number of microstates, okay? So the entropy of the gas in the lecture hall would be equal to the Boltzmann's constant times natural log of the number of microstates compatible with that macrostate. Okay. Now this number is of course very hard to calculate, and in practice, so it's very hard to calculate. And so we don't use this in engineering applications. We do not use this expression for calculating entropy. We use this expression for calculating entropy, change in entropy. Okay, here you can calculate the absolute value of entropy. Again, Mr. Boltzmann derived this expression, and Boltzmann was an extremely smart fellow. And so on his tombstone, that is the epithet. Okay, so that's how proud he was of this expression. All right, so I will quickly go over some of these points, and I'll let you guys read the slides. Okay, so the question is the following. Okay, let's go back to the drawing board. Okay, so here's the statistical point of view. Okay, so let's say this end of the room is hot and this end of the room is cold. Okay. So you saw, oops. So this end of the, okay, so this end of the room is hot and this end is hot and this end is cold. You know that of course heat will flow in that direction. Okay. And till when will heat flow? Till let's say the entire room comes to the same temperature. Okay. Now the question is, why does this happen? Okay, so what the reason this happens is when the system goes from this macroscopic state to this macroscopic state, this system has many more microstates. Okay, and so the system okay. And so the system evolves towards, so a system evolves towards a macro state. So this, you see, this is a macro state, this is a macro state. A macro state is where you're describing the system with macroscopic variables. So the system evolves from this macro states to this macro state. So a system evolves towards a macro state which has the greatest number of microstates. So that is the statistical statement. Greatest number of microstates. Okay. So that's the statement, and that's the greater the microstates, the greater the entropy. Okay, so that's what this equation was. W is the number of microstates. So the macrostate with the maximum number of microstates is the state it evolves towards. Greater the microstates, greater the entropy. And that's what the second law of thermodynamics is. All right, so we'll illustrate this using this simple example. Okay. So you guys all intuitively know this. Okay, so here's a room filled with gas. And the question is, why do you not see all the gas move to one side of the room? Why do you always see the gas always evenly spread out in the room? The question. Why do you never see this? And you always see this. Okay. So here's the answer to that. Okay. Well, this is possible. It's just that the probability of this occurring is so low that it's negligible. Okay. And the probability of this occurring is extremely high compared to this probability. And so that's why you see the system in this configuration at all times. Okay. And so we'll see what is the probability of this occurring. And that's what this simple calculation is about. So let's say, so going back to this, okay. So let's do it one molecule at a time. What is the probability of having one molecule in this on the left side? It's 1/2. What is if you had two molecules, what's the probability of both of them being in this half? It would be 1/2 to the power squared. If you had three molecules, if you had, let's say, 50 molecules, the probability of all 50 being there would be, or let's say 100 molecules, it would be 1/2 to the power 100. Okay. And that's what this slide shows you. So let's say if you had n molecules, the probability of having all n molecules here is 1/2 to the power n. Okay. So that's how small the probability is. And in comparison, the probability of all the molecules being evenly spread out would, I mean, the relative probability would be 1 compared to this. Okay. Okay, so if there are 100 gas molecules in the system, the probability of all 100 molecules being in this side is 10 to the minus 31. okay, or roughly 10 to the minus 30. Okay, that's how small a probability is with only 100 molecules. Now, if you have a Avogadro's number of molecules, the probability of all Avogadro number of trillion molecules being here would be 0 essentially. Okay, so now here's the statement. This is called the ergodic hypothesis, and what this states is if the system spent 1 second per microstate, this would take, it would take 10 to the 13 billion years, where the age of the universe is 10 billion years. Okay, so what we're saying here is in 10 to the 13 billion years, the system would spend 1 second in this configuration, and all the rest of the time in with the molecules evenly spread out. So that's how small the probability is of the system coming in this configuration. Okay, so that's the statistical answer for why all processes occur only in the direction in which entropy increases. Okay. So although the probability that this process will happen is not 0, it's so small that we can treat it as 0. So we conclude that second law of thermodynamics is never violated as in any practical situations. Okay, so this, if all the air moved over here to one side of the room, that would be a violation of the second law of thermodynamics. Okay. So, so the number of microstates with all air molecules in one side of the room is next to 0 compared to the air evenly distributed throughout the room, and that's why. So this is showing you the number of microstates. Okay, so the number of microstates with the air evenly distributed is so large compared to it being all in one side that this stuff never happens. Okay, this goes through a calculation showing you the derivation of this formula, okay, which is sort of a very simplistic derivation of Boltzmann's formula. Okay, so the Boltzmann's formula allows you to calculate the absolute value of the absolute value of the entropy of a system if you could calculate the number of microstates. Okay, and like I said, almost all the time, we're not interested in this calculation. All we're interested in calculating is the following: change in entropy. So, and this is the expression we'll use to calculate the change in entropy of a system. Okay. We do not use this expression. Okay. All right, so that's Boltzmann's formula, and that's what he is most proud of. Now we'll talk about heat engines, but let's take a 2-minute break. Okay.